Hello dear friends, welcome to my channels. Today's discussion is linear algebra. Consider the non-homogeneous system of linear equation ax equals to b, where a is m cross n and x belongs to r to the power n and b belongs to r to the power m. Then the corresponding homogeneous system ax equals to 0 has unique solution ax equals to b has infinitely many solutions for each vector b in r to the power m. Number 2, the corresponding homogeneous system ax equals to 0 has no non-zero solutions. There is a vector b in r to the power m for which ax equals to b has no solution. The correct code 1 and 2 are true. 1 true, 2 is false. No, 1 and 2 is false. So friends, our first statement is display. I am talking about first statement. Given A is m cross n, consider 3 cross 2 matrix. Then ax equals to 0 has unique solution that implies rank of A equals to 2. Suppose rank of A is 1 0 0 1 0 0. So rank of A, this matrix is 3 cross 2, means 3 is row and 2 is column. The number of unknown variable, and now b is we can write this is a, and b is number of unknown variable is 1 0 2, number of unknown variable. So here matrix augmented matrix A such that b can have rank 3 is rank A does not equals to augmented matrix rank of the augmented matrix A such that, so this is the, suppose this is the augmented matrix, so this is A such that B, and rank of A such that B equals to 3. So rank of A does not equals to rank of A such that B. That's why this means no solution. So the corresponding homogeneous system ax equals to 0 has unique solution and B has infinitely many each vector B in r to the power m. So this is false. And number 2, the corresponding homogeneous system ax equals to 0 has a non-zero solution. There is a vector b in r to the power m for which ax equals to b has no solution. So there is a theory, every homogeneous equation has either unique solution, either trivial solution, or infinitely many solutions. Can't say no solution. So this option is also. So recapitulation, if rank A equals to n, means number of recapitulations for homogeneous equation. If rank equals to number of unknowns, then the system only the trivial solution. And number 2, this is the number 1, and number 2, if rank A less than n, so number of unknowns, then the system has an infinite number of trivial solutions. So friends, whatever we see, that infinite number of non-trivial solutions. And another recapitulations, because this is also important for remember, we have to recapitulate. If it is non-homogeneous, if of non-homogeneous Homogeneous linear if rank of augmented matrix A such that B does not equal rank of A equals to number of then the system is no solution if rank of A such that B equals to rank of A equals to number of unknowns, rank of A equals unique solution, and if rank of augmented matrix A such that B of A equals to number of unknowns does not less than number of unknowns then the system infinite solution. I hope that you can understand. So friends, our next problem is t such that r to the power 7 tends to r to the power 7 be a linear transformation such that t square is equal to 0, the rank of t. If t square equals to 0, then image P is proper subset of car T. So in particular, the rank of T is not more than the nullity of T. Since the sum of rank and nullity is 7, the sum of rank and nullity is 7. We conclude that rank of T is 3 or smaller. So here's an example of the matrix of a rank C. Transformation of with the property that t square equals to 0. Our example is that 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. This is our matrix. Here this is E and rank of E is equal to 3, E square is equal to 0. Since T such that r to the power 7 subset of kernel T, so we can conclude that rank of T is then equals to dimension card T is equal to 7 minus rank T. So rank T obviously less than greater than less than equals to 3. So we solve this problem. Next, our problem is this question number 3. Let V be the vector space of 2 cross 2 matrices over R, and let B equals to 1, 0, 2, 3. Let T such that V be a linear transformation defined by T such that AB minus BA. Find the basis of dimension and T. Solution. To find the kernel A of capital T, we have to find A, B, C, D in capital V. That is T, A, B. Sorry, it is for my convenience. It should be in here. B is C. A, C, B, D, because in the formula T, A, my A is A, B, C, D. So T, A, B, C, D equals to 0, 0, 0. Okay. Now T, A, B, C, D equals to A, B, C, D into 1, 0, 2, 3 minus, because B is 1, 0, 2, 3, because T, A is equal to A, B, A, B minus B, B, A. So I put in here 1, 2, 0, 3, A, B, C, D. Okay. After that, the multiplication, we have A into 2A plus 3B and C plus 2C plus 3D minus A plus 2C plus 3C plus B plus 2D into 0 into 3D equals to minus 2C minus 2 plus 2A plus 2B minus 2D 2C equals to 0, 0, 0, 0, 0. After that, we get the value C equals to 0, A plus B minus D equals to 0. So friends, the three variable are three variable are B and D. Three variable are B and D. So dimension of K equals to number of free variable equals to 2, and if b equals to 1, so b equals to minus 1, d equals to 0, so a equals to 1. If b equals to 0, 1, so a equals to 1. So my set is 1 minus 1 0 0 and 1 0 0. They are kernel capital T. Next friends, we are going to solve question number 4. Let u equals to x belongs to r to the power 4 1 0 0 2 3 0 0 minus 1 5 0 0 10 0 and v span is equal to 1 1 by 2 and minus 2 0 1 0. Give 4 vectors in each of u and v. V is the set of linear combination. V is set of linear combination of V is set of linear combination of 1 1 by 2 0 minus 1 minus 2 0 1 comma 0. And so friends, we can construct 4 vectors are minus 2 0 1 0 1 comma 1 by 2 0 comma minus 1 belongs to V. For that we can use a linear combination. We can get minus 1 1 by 2 1 minus 1 belongs to V. Next is 1 1 0 5 0 2 3 and 0 0 minus 1 0 10 0. Multiplying with 0 0 0 0, we can get 0. So 0 comma 0 comma 0 belongs to U. Similarly, if we multiply 0 comma 1 comma 0 comma 0 also belongs to U, as 1 0 5 0 0 0 2 0 10 3 minus 1 0 cross 0 1 0 0 equals to 0. Again we will multiply 105 0 0 0 2 0 10 3 minus 1 comma 0 into 0 3 double 0. Similarly we can get 0. So my four vectors are 0 3 0 0 comma 0 comma 0. We have to construct, and 0 1 0 comma 0 equals to 0. So it is 2 0 minus 1 comma 0. So this is my total u. So I have found the u and v vectors. Now next is determine which of the following sets are subspace of RQ. Number A. This is a subspace since this portion since it is the set of solution. It is the set of solution to a homogeneous linear equation. So this is the homogeneous linear equations as x plus 2y minus 3z equals to 0. This is homogeneous linear equations, friends, so that it is subspace. Next is number B. So number A is correct. Number B, E comma B comma C belongs to greater than or equals to 0. So the vector one comma 1 is in the set, but minus 1 into 1 comma 1 is not in the set. Is not in the set. So the set is not a subspace. It's not a subspace. Is not a subspace since it is not closed under scalar multiplications. Since it is not closed in the scalar multiplication. So this is my option B. Now option B is not a subspace. Option C. Let's try option C. If 0 alpha plus 1 belongs to RQ, if 0 comma 0 comma alpha plus 1, then alpha equals to 0, but alpha plus 1 does not equals to 0. So that this is not subspace. Option D. A main belongs to R cube and k square is equal to n square. Then 1, 0, 1 is in the set since this is the option E. Option D we will discuss very soon. Since 1 square equals to 1 square, 1 square equals to 1 square, and 1, 0 comma minus 1 is in the set since 1 square equals to 1 square, but 1, 0 comma 1 and 1, 0 comma minus 1 plus equals to 2 comma 0 is not in the set. Is not in the set since 2 square is equal to 0 square. So this is not subspace. This is not subspace. So friends, this portion is not subspace, but this is subspace. This portion is subspace as the base is 1, 0 minus 2 and b 5 comma 7 is possible. Number 6. Find a basis for the subspace V equal to x belongs to R cube, Ax equals to 0, where A equals to this. Also write the dimension. Okay. Friends, we need to learn what is subspace. That also I need to discuss. A set V is a subspace of R to the power n when number 1, 0 belongs to V, number 2 U plus V belongs to capital V, and number 3 if U bar belongs to V and C belongs to R, then CU bar belongs to capital V. If V the set of solution of homogeneous linear equation, then V is subspace. If V is span of some vectors, then V is subspace. So if V is the set of solution to homogeneous equation, then V is subspace, and if V is span of some vectors, then V is subspace. So friends, that's why we see that this is the span of two vectors of 1 0 comma minus 2 and 5 comma 7. That's why this is subspace. So friends, I hope I can clear this concept. Next problem, please. Question number 6. Find the basis for the subspace V equals to x belongs to R cube and Ax is equal to 0, where A equals to 205, 1 comma minus half. Also write down the dimension. So a basis for capital V is a set of vectors in capital V, which, so friends, Ax equal to 0. So 2 0 5 1 1 and minus half. So now R1 equals to half R1. So what we get? 1 0 5 by 2 and 1 1 minus half. After that we get 1 in here. My operation is R2 equivalent to R2 minus R1. So we get 105 by 2 0 1 3 by 2. Next is x3 equal to t. Okay, we kept it left. We will solve it after few time later. Now question numbers 7. We will solve question number 7. Find a basis for the subspace u equal to xyz and 3x plus y minus 70 0. Write down the dimension of u. A basis for u is a set of vectors in U which number 1 and number 2 are linearly independent. So 3x plus y minus equals to 0. So we get x minus 3x minus plus 70 comma t comma z comma t. So our vectors should be x 1 comma minus 3 comma 0 comma 0 plus t equals to 0 comma 7 comma 0 comma 1 plus z equals to 0 comma 0 comma 1 comma 0. So dimension, so bases are 1 comma minus 3 comma 0 comma 0 0 comma 7 comma 0 comma 0 1 and 0 comma 0 comma 1 comma 0. So this is the 3 dimension is 3. So this is my answer. Dimension and dimension basis. Now next, find a basis for write down dimension of subspace W equals to span of this. A basis for W is a set of vectors in W which number 1 span W, number 2 are linearly independent. The dimension of W is the number of vectors in a basis for W. Now the bases are 2 by 3, comma 0, comma minus 5, minus 3, minus 2. Minus 3, minus 2, comma 0, 15, 3, comma 0, comma minus 1, minus 2. So it can be written this way. Two by 3, 0, comma minus 5. This row form the transposition form or a transposition form. I have to write. -3 -2 0 and 15 3 0 1 and 1 by 2. After that we can write 7 by 2 1 by 3 -1 -2. So R1 equals to 2R1, R2 equals to 3R2, R3 equals to -R3, and R4 equals to 2R4. After that we can write this way: 2 -6 6 7, 2 -6 0 1 0 0 1 -1 minus minus plus. Here is writing mistake. This is -1 and -10 31 -4. So friends, we see that R4 is equal to 2R4 new. New case R2 equals to R2 minus R1 and R4 equals to R4 plus 5 R1. Okay, R2 minus R1. So whatever we get, if any calculation mistake, please tell me. So we get this is 2 minus 6 6 7, and this is 0 0 minus 6 minus 6. After that 0 0 1 1 0 0 31 31. So friends, we get 2 minus 6 6 7. So in here and 0 0 1 1 0 0 minus 6 minus 6 0 31 31. So whatever I am doing, R3 equals to R2 and R2 tends to R. So friends, next I am doing R1 equals to R1 minus 6 R2, R3 equals to R3 plus 6 R2, R4 equals to R4 minus 31 R2. So we get 0 minus 6 0 0 0 0 1 0 0 1 1 0 0. So friends, we get this value, and after that we see that this portion and this portion, this portion are at the base. So columns that become pivot columns that become pivot columns are the basis So a basis for W is, so a basis for W is, you see that these two this 2 is my basis. So I can write these two vectors as well on basis form. So our basis is 1 comma 2 by 3 comma 0 comma minus 5 3 comma 0 comma minus 1 comma dimension of W is 2. Now we are going to solve next problem. The subspace V of R cube contains the vector 0 2 minus 1 root 3 comma 0 0 but does not contain the vector 0 1 minus half. Find the dimension of a basis for V. V contains early independent two linearly independent vectors two linearly independent vectors. So dimension of V greater than equals to 2. So V does not contain all vectors in R3, the subspaces, and but does not contain the V does not contain the V does not contain all vectors in R cube. All vectors in capital R cube. So friends, so dimension of V does not equals to 3, and therefore dimension of V equals to 2. The vector the vectors 0, comma 2, comma minus 1 and root 3, comma 0, comma 0 are linearly independent and span two dimension of subspace. So a basis for V is 0, comma 2, comma minus 1, comma root 3, comma 0, comma 0. This is my basis. So friends, I hope it is clear. This is the main fact that these are two linearly independent because contains the vector, but this problem is not include because they are linearly independent, but therefore their basis, so two bases, and this is not include. That means that are not all vectors does not contains in V. This is means that there is a kernel, and that's why dimension of V is 2 and basis is also 0, 2, comma minus 1. I hope it is clear. Now the next problem, questions number 11. Let LRn be the subspace of R and linear maps from R to the power n to R to the power n if car T LRn be the subspace of R and linear maps from Rn to Rn if car T denotes the kernel of null space of T, then which of the following of true? Number 1, there exists T belongs to L R to the power 5 such that range T is equal to cut T. There does not exist L R to the power 5 0 such that range T is equal to not cut T. There exists T belongs to L R to the power 6 0 such that range T is equal to cut T. Does not exist T belongs to L R to the power 6 such that range T equals to cut T. Range, now the solution is that range and rank of T. Range and rank of T. Range T is equal to Tx, and x belongs to capital R, and rank of T is equal to dimension of range T. Now kernel and nullity of T of capital T. Car T equals to x belongs to R, Tx equals to 0, and nullity T equals to dimension of card. Rank-nullity theorem. Rank-nullity theorem. Rank T plus nullity T is equal to dimension of domain. So for r to the power 5, for r to the power 5, rank of T plus nullity is equal to dimension equals to 5. So if range T equals to car T, then rank of T equals to nullity of T, nullity of T equals to so that 2 of rank T equals to 5. So rank T equals to 5 by 2. That is not possible. This is not possible. So first option is wrong. There exists T belongs to r to the power L r to the power 5 such that range T, and this is wrong because we see that both are 5 by 2, not possible. Not possible. Next, for r to the power 6, rank of T plus nullity T equals to 6. So rank of T equals to 3. For r to the power 6, example T such that T x1, x2, 2 x6 equals, okay, so this is possible. So my next option, there does not exist such as r to the power, this is correct. Number 2 is correct. There does not exist and r to the power 6 has the this is correct, this is false, sorry, this is not false, this is true, and this is true, and this is false. So I hope I can clear. So the Rank-nullity theorem. So take the any example. So I just want to say example. You can take any 0 comma 0 comma 0 x1 x2 x3. This is my vectors. So our range t equals to 0 comma 0 comma 0 1 comma 0 comma 0, this is 1, and 0 comma 0 comma 0 comma 0 comma 1 comma 0, and 0 comma 0 comma 1, this is, and another is kernel car t equals to x such that tx equals to 0. It may be 1 comma 0 comma 0 comma 0 0 0. This is my x value. It can be written this way, and another is 0, and another is 0 comma 0 comma 1 comma 0 comma 0. So if you put this in here, this vector space, this vector space 0 comma 1 1 comma, so it should be 0. All are, oh sorry, it is x1 x2 x3. Yeah, product result is this is x3. So car t should be 0 comma 0 comma 0 a, because then it is 0, because all the values are 0. So this is my vector. This kind of vector can be possible. Number 12, dimension of vector space of all symmetric A equals to Aij with real entries A11 equals to 0 and trace equals to 0. So friends, dimension of matrix is n into n plus 1 divided by 2, and two restriction, one is A11 equals to 0 and trace a theory that dimension of subspace equals to dimension of vector space minus restriction. So dimension of vector space n into n plus 1 divided by 2 minus 2 restriction, and this will become n square plus n minus 4 divided by 2. So I hope I can clear this concept. Next problem is question number 13. Dimension of the subspace W is equal to 3x1. This is the r to the power 5 r. So total variable is 5, and free variable equals to 1, or you can say number of restriction equals to 1. So dimension of the subspace is equal to 5 minus 1 equals to 4. So my answer is 4. Next, eigenvalue of a equal to minus 1 comma 1 2 comma minus 2 and b equals to a to the power 4. A to the power 4, this is minus 5 square plus 5i. So det a plus b equals to 0, det b equals to 1, trace a equals to 0, trace a plus b equals to 4. So total eigenvalue of b equals to 1 minus 5 plus 5 equals to 1. This is in case of minus 1. In case of b, lambda means b1, lambda equals to 1, b1 equals to eigenvalue EV b1 equals to 1 minus 5 plus 5 equals to 1, and b2 eigenvalue EV b2 equals to 16 minus 20 plus 5 equals to 1, and eigenvalue of p2 equals to 1. So friends, we see that all the value of eigenvalue is 1. So there is no value is at 0. So det a plus b equals to 0 is not possible. One minute. Det a plus b equals to 0 is possible. How? Because a plus b eigenvalues are we can add because they are commutative. Okay. So friends, eigenvalue of b minus 2 b minus 2 is also 1. So this is I get, and now we see that a plus b, a plus b, let a plus b equals to minus 1 plus 1, because we get when it is the value is minus 1, eigenvalues is minus 1, then we get 1 is plus 1. So after all we get 0. So det of a plus b equals to 0. So option 1 is correct. Option 2, det b equals to 1. Now we have to see that eigenvalue of b, eigenvalue of b is 1. So det b equals to 1. This is correct. So option 2 is correct. A equals to 0. So it is also correct. It is also correct because trace A equals to sum of eigenvalue it is 1 minus 1 plus 2 minus 2 equals to 0. So it is correct. Trace A plus B, trace A plus B, that is 2 plus 1 and 2 1. So 2 0 3 1, I think. 0 2 3 minus 1. So eigenvalue 2 3 minus 1. So trace of A plus B is equal to 4. Now we will discuss question number 15. Let V be the vector space of polynomial in the variable t of degree at most 2 over R. An inner product of V is defined by f comma g is equal to 0 to 1 ft gt dt, and for f comma g belongs to V, let w equal to span 1 minus t square divided by 1 plus t square, and w perpendicular be the orthogonal. Complement of w in V, which of the following condition is satisfied for all h belongs to w perpendicular. H is event function, that is ht equal to minus h minus t. H is an odd function, that is ht equal to minus h minus t. Ht equals to 0 has a real solution, h0 equal to 0. So friends, we need to know orthogonal vectors. So important concept, we need to know orthogonal vectors u and v are orthogonal if u comma v equals to 0. Orthogonal complement. The orthogonal complement of a subspace W of a vector space V is the set W perpendicular of all vector in V that are orthogonal to every vector in W if small w belongs to capital W perpendicular, then WU equals to 0. For every U in W. If HT equals to A plus BT plus CT square belongs to W, then H 1 minus T square equals to 0. H 1 plus T square now integration 0 to 1 A minus AT square plus BT minus BT cube plus CT square minus CT cube into DT equals to 0. So we get 2A by 3 plus B by 4 plus 2C divided by 15 equals to 0, and 40A plus 15B plus 8C equals to 0. Similarly, H, 1 plus T square equals to 0. So we get A plus BT plus CT square into 1 plus equals to 0 DT equals to 0. So we get the value is 4A divided by 3 plus 3B divided by 4 plus 8C divided by 15 equals to 0. So we get 40A plus 15b plus 8c equals to 0. So friends, take c. So we can write a equals to 1 by 5c, b is equal to c by 15c. So if we are putting this value, then this is minus. So we can get that 8a minus 16c, 8c minus 16c plus 8c equals to 0. So my equation holds and we get this value. So whatever we get, ht, so our ht, we just putting the value ht, then ht equals to c by 15 into 3 plus 3 minus 16t plus 15 t square. So h minus t is equal to 3 by 3 c by 15 t plus 16t plus 15t square. Now my question is incoming that h is an even function. So h is an even function. This is not possible because we see that it is not possible. H is odd function. This is not possible. ht is equal to 0 has a real solution. Obviously ht equals to 0, if it is 0, has a real solution. It can be possible, it can be possible, and h0 is equal to 0, it cannot be possible. So friends, I hope I can clear this concept. Next problem is a be a real matrix with characteristics polynomial x minus 1 whole cube. So a is necessarily diagonalizable. If the minimal polynomial of a is x minus 1 whole cube, then a is diagonalizable. Characteristic polynomial of a square is equal to x minus 1 whole cube. If a has exactly 2 Jordan blocks, then a minus I whole square is diagonalizable. So this problem is very, very important. So let's start to solve this point. For a is necessarily diagonalizable. For one, option option 1, for option 1, counter example equals to 1 1 1 0 0 1 0 0 0 1 1. This is my a, and date a, date lambda minus I minus a equals to date of lambda minus 1 minus 1 minus 1 0 0 lambda minus 1 0 minus 1 lambda minus 1. So we get the characteristics equation is lambda minus 1 whole cube. So my first option, eigenvalues are eigenvalues 1 comma 1 comma 1. A is diagonalizable if its algebraic and geometric multiplicity are equal for each eigenvalue. So AM equals to GM, then it is diagonalizable. So let's check its geometric multiplicity. So algebraic multiplicity, AM algebraic multiplicity is 3. So GM of 1 equals to n minus rho into a minus lambda I. So n equals to 3 in here, and rho into lambda minus I equals to this portion rho, and 0 0 0 we get 1 1 0 0 0 and 1. This portion 3 into rho into a minus I, so this rank is 2, so gm equals to 1. Geometric multiplicity, that is number of eigenvalue, number of eigenvector, sorry. So therefore a is not diagonalizable. a is a is not diagonalizable. So this statement is false. It's not necessarily diagonalizable. If the minimal polynomial a is equal to x minus 1 whole cube, then it is diagonalizable. So minimal polynomial is x minus 1 whole cube. So number of Jordan block, minimal polynomial equal to x minus 1 whole cube. So friends, a minimal polynomial is x minus 1 whole cube. So let's, in case of this matrix, Jordan block equal to lambda, lambda, lambda. Sorry, it is not 3 cross 3 matrix I take. So this is my Jordan block. JC block, and my is my 1, and all portion 0 0 0 0 0. So this is my Jordan. Now minimal polynomial equals to lambda minus 1 whole cube, and JC block is equal to this is the JC block, and number of JC block is equal to number of JC blocks, means Jordan canonical block, is equal to minimal number of linear independent vector pendant eigenvector that equals to geometric multiplicity. This is called geometric number of Jordan canonical block is equal to geometric multiplicity. So friends, I hope I can clear this concept. Now in here we see the JC block is equal to 1, so GM equals to 1, and AM equals to 3, so AM does not. So second option is also false. This is false, that if the minimal polynomial of a is x minus 1 whole cube, then a is diagonalizable. This is false. Number 2, characteristic polynomial of a square is equal to x minus 1 whole cube. If a characteristic for eigenvalue is 1, so a square eigenvalue equals to also 1. So obviously character of a square is equal to 1. If A has exactly 2 Jordan blocks, then A minus I whole square is diagonalizable. So this option is correct. This option is correct. This is not false. True. This is true. So I write it correct. Number 4. A minus I equals to A is 3. Number 1 question we will go. That is my question. A has exactly 2 Jordan blocks. Then A minus I whole square is diagonalizable or not. So friends, 2 Jordan blocks. So for case JC block 0 1, this is one possible. Another is only 1. I can write way. So this is this function JC block. So JC2. So my I can write A equals to 1 0 0 0 1 0 and 0. Sorry, it is not 1. This is 1 0 0 1. So A minus I equals to 0 0 0 1 0 0 0. So this is my A minus I. So A minus I whole square, A I whole square equals to 0 1 0 0 0 0 0 0 0 0 into 0 1 0 0 0 0 0 0 0. So matrix multiplication is this way. So we get all 0 after the 0, and after all this is also 0 0, this is also 0, and this is also 0 0 0. So this is my diagonalizable. This is matrix is diagonalizable. So friends, so this option is friends correct. We are choosing very small matrix with 3 cross 3 matrix. We can choose also 7 cross, but this is not good. We have to choose this way. According to I give some example, and after that we get 3 and 4 is correct. Next problem, friends. Let A and B be real invertible matrix such that AB equals to minus BA, trace of B equals to 1, and trace of A, trace of B equals to 0, trace of A equals to 0, trace of B equals to 0. So friends, this problem is very interesting. So A and B let A and B be real invertible matrices such that AB is equal to minus B. Then trace of A equals to trace B equals to 1, trace of A equals to trace B equals to 0. So friends, I have to solve this kind of problem. So solution. So AB equals to minus BA. Okay, this is the number 1 point. So trace of AB minus trace of B. Okay, I hope I can clear. After that, A and B, both are real invertible. So inverse exists. A is invertible, and B is also invertible. So date A does not equals to 0, and date B does not equals to 0 if it is invertible. So I can write this way: trace of AB equals to minus trace of AB, because both are invertible, so it is commutative. AB equals to BA, we can say. So that 2 trace of AB equals to 0. Now friends, B inverse A AB equals to minus B inverse BA equals to minus A. So B inverse AB equals to minus A. That means it is similar matrix. Similar matrix. So in case of similar matrix, trace of A equal to minus trace of A. So 2 trace of A. So whatever we get, 2 trace of A equals to 0, and similarly trace of B equals to 0, as B and equivalent to similar to minus B. So B similar to minus B, so trace of B equals to 0. So my option 2 is correct, and this of option 1 is wrong, option 3 is wrong, option 4 is wrong. So only this option is correct. Next, let x, y, z be basis of R cube. Consider the following statements P and Q. X plus y plus z, x minus z is basis of R cube. X plus y plus z, x plus 2y, and x minus 3z is basis of R cube. Which statement is true? Now solve this kind of problem. X, y, z is basis of capital R cube. So now we see that they are independent, linearly independent or not. So I can write this way: A x plus y plus b y plus z, c x minus z equals to 0. C x minus z. So A minus c x equals to 0. So we get A equals to c. This is one, and another is A plus b Similarly, we can get a plus b equals to 0. So a equals to minus b, and b plus c. So b equals to, I get this vector. This is, so I can write c equals to 1. So b equals to minus 1, and a equals to 1. So I cannot say they are not 0. So this number p is basis. This is false, because it should be a equals to 0, b equals to 0, b does not equals to 0, and c does not equals to 0. So it is not li, linearly independent vector. I hope I can clear this concept. Next, we will go number q. A x plus y plus z plus b x plus 2y minus c plus c x minus 3z equals to, so a plus b plus c equals to 0, and comparing coefficient of the x, coefficient of y, coefficient z, and a plus 2b equals to 0, a minus x minus, this is the z, yeah, okay, a minus b minus 3c equals to 0. So whatever we get from this equation, if we multiply, I can write this equation is 1, this equation is 2, and this equation is 3. So we get 1, 2, 3, that 4a, just simple calculation, a minus b divided by 3 equals to c, we get. So putting this value in here, a plus a minus b by 3, 4a plus 2b equals to 0. And now you see that a plus 2b equals to 0. So both are equals to 0, also c equals to 0. So this vector is false, this vector is correct, this option is correct, this is basis, this is true. Question number 19. P and Q. M is an n cross n complex matrix, then Rm equals to nullity of M star is equal to perpendicular, and there exists a unitary matrix with an eigenvalue lambda such that mod of lambda less than 1. Which statement is true? M is n cross n complex matrix, and Rm equals to range of M equals to n M star orthogonal complement. This is called orthogonal complement, and this null space of null space of M conjugate. Now range space of M equal y belongs to C to the power n for there exists x belongs to C to the power n such that mx range matrix and equals to x belongs to C to the power n such that it is not, it is z belongs to C to the such that x comma z null m star complement and it is null m star complement orthogonal complement. This is the null m star complement, but null m star equal x belongs to C to the power n and m star means m conjugate x equals to 0. So let y belongs to Rm range of so mx is equal to y x let x dash belongs to null m star that implies x comma x dash comma y equals to dash comma mx x dash belongs to nm star equal to x dash y equals to x dash mx and mx star x dash x star m star x dash equals to x star dot 0 equals to 0. Now rank of M is the proper subset of nullity of M star. Similarly, let nm star perpendicular, then that implies x comma y all x belongs to n m star so m star x equals to 0 and y star x when m star x equals to 0. So we can prove is subset of range M. So we can say that Rm range of M equal to nullity T of M star. So my first option there exists a unitary matrix with an eigenvalue lambda such that lambda less than 1 This statement is totally false. This is false. How this statement is false? Now the questions. So unitary matrix, you have to learn. Question is that unitary matrix, there exists a unitary matrix. So what is the unitary matrix, friends? A star, a star equals to s equals to I, where a star is conjugate matrix, conjugate transpose of conjugate transpose of a matrix, conjugate matrix, conjugate transpose of matrix A. So this is the A star. Now AV equals to lambda V, and lambda equals to A plus IV. UV equals to V star U. I can write this way. Lambda star lambda, lambda to lambda mod of lambda whole square, and V star A, V star A star equals to lambda star V star. Now multiplying, this is the equation 1 and this is equation 2. So from 1 and 2 we have V star A star V star A star A equal A V equals to lambda lambda star V star into lambda V. So friends, A star is equal to 1. So we get V star into V star lambda into V star V. So V star V into lambda into V star V. We can write this is as the norm of V whole square is equal to mod of lambda whole square norm of V whole square. So I get lambda square equals to 1. So norm of lambda equals to 1. So it cannot be less than 1. So friends, I hope I can clear this statement is false. Lambda less than 1. This statement is false. Next is consider a real vector space V of dimension n and non-zero linear transformation T such that V tends to V if dimension TV less than n and T square is equal to lambda T for some lambda belongs to R by 0, then which of the following is true? So I have to find out this kind of problem. So friends, that dimension of TV, so there exists the dimension that T, okay, T is invertible or not. So dimension on TV less than n, that means nullity TV does not equals to phi, and T square equals to lambda t, that means x square minus lambda x equals to 0. So x equals to x minus lambda equals to 0, that is 0 if lambda does not equals to 0. So this portion is totally wrong, because date t does not equals to lambda to the power n, date t is equal to 0, because lambda to the power n, it is not possible. T is invertible, this is also not possible. There exists a non-trivial subspace of v1 of b such that tx equals to 0. So this is correct, this portion is correct, and lambda is only eigenvalue. This portion is also wrong, because eigenvalue is also eigenvalue. So this probably so p is in, lambda is only eigenvalue, this is not possible. Number 20, question number 21. Let T such that r to the power 4 tends to r to the power 4 the linear map defined by x plus x comma y comma z comma w, and then the rank T is equals to rank. So whatever we get T equals to x plus z, 2x plus y plus 3z, 2y plus 2z comma w. So our basic E1 equals to 1 comma 2 comma 0 comma 0, PE2 comma 0 1 comma 2 comma 0, TE3 equals to TE3 equals to 1 comma 3 comma 2 comma 0, TE4 equals to 0 comma 0 comma 0 comma 1. So my T matrix is, I can write this way: 1 2 double 0 0 1 2 0 1 3 2 0 0 0 0 1. This is my matrix. So how can I get rank? After that I will operating row column operating. So I get 1 0 0 0 0 1 1 1 0 0 0 0 0 and 0 0 1 I get, and my rank is equals to, this is my answer. Next problem. Next problem is question number 22. Let m equals to 1 0 0 1 1 1 0 1 1 and e to the power m equals to I plus m square by 2 plus 0 up to infinity. If e to the power m is equal to bij, then 1 by e, I equals to 3, j equals to 1, bij is equals to, I have to find out. So how can I find out? M square equals to 1 to 1 to 1 0 1 2 0 0 1, just multiplying, and m cube equals to 1 0 0 0 6 4 1, m to the power n divided by n factorial equals 1 by n factorial divided by 1 0 0 n 1 0 half into n plus 1 n 1. We get the formula series. We use the series formula. E to the power m equals to summation equals to n equals to 0 to infinity m to the power n divided by n factorial, m to the power n divided by n factorial equals to summation n equals to 0 to infinity 1 by n factorial 1 0 0 n into n minus 1 divided by 2 n 1. Summation n equals to 0 1 by n factorial summation n equals to 0 to infinity 1 by n minus 1 factorial summation n equals to 0 to infinity 1 by n minus 2 factorial 1 by 2. After that, in here you get 0 0 summation 1 by n factorial and summation n equals to 0 to infinity 1 by n minus 1 factorial. This is 0 and this is summation n equals to 0 to infinity 1 by n factorial. So friends, this is my total. So I get this value is equals to e e half e half e 0 0 e 0 0 e. So my answer should be 1 by e, and my total e is 5e plus half of e is equal to 11. So friends, now in number 23. Let W equal to span 1 by root 2 0 1 comma 1 and 1 by root 2 be subspace of the Euclidean space r to the power 4, then the square of the distance from the point W is equals to. So T, so span is span equals to 1 by root over 2 0 comma 0 comma 1 comma 1 and 1 by root 2 1 comma minus 1 comma 0 comma 0, and point P equals to 1 comma 1 comma 1 comma 1, and so this point equals to can be written this way: x by root over 2 0 comma 0 comma 1 comma 1 plus y by root over 2 1 comma minus 1 comma 0 comma 0. So it can be written this way: y root 2 y by root 2 minus y by root 2 comma x by root 2 comma x by root 2. So d square equals to y by root 2 minus 1 whole square plus x by root 2 minus 1 whole square plus x by root 2 minus 1 whole square. So is d, and now we derivative differentiate with dx, then dx is 2 into 2 x by root 2 minus 1 into 1 by root 2 equals to 0, and I get x is equal to root 2, and dy equals to, we get y dy equals to 0, and after differentiation we get y equals to 0. So d square is equal to 1 plus 1 plus 0 plus 0 equals to 2. So friends, my answer is 2. Next, T such that R to the power 4 tends to R to the power 4 be a linear map such that null space of T is x, y, z, comma w is equal to x plus y plus z plus w, and rank of T plus 4I is 3, and the minimal polynomial of T is x plus x into, so alpha value of the alpha. So how can I get the value of alpha? So x plus y plus z equals to z, x plus y plus equals to w equals to 0, and rank equals to 3. So my nullity, which rank is T minus 4I, so it is nullity, and eigenvalue value is 4, and gm equals to 4 minus 3 equals to 1. Geometric multiplicity is equal to 4 minus 3 is equal to 1. This is the number of Jordan block. Number of JC block, equals to 1. Number of JC block equals to 1. So minimal polynomial polynomial equals to x into x minus 4I whole to the power 4 whole to the power alpha. Find out the value of alpha. So number of JC block is 1, means only one block I can set up only one block. So nullity, now x plus y plus z plus w equals to 0. So number of free variable able is 3. So dimension nullity equals to 3. So my characteristics equation will be x cube into x minus 4 is characteristic equation, and minimal polynomial equals to x into x minus 4. The matrix is, so alpha is equals to 1, and eigenvalue is 0 comma 0 comma 0 comma 4. It is diagonalizable as the minimal polynomial is linear factor, and number of Jordan block will be, JC block is 0 0 0 4. This is my JC block. JC block equals to this. Next, question number 25. MP 3 cross 3 singular matrix, and suppose that 2 and 3 are eigenvalues of M, then the number of linearly independent eigenvalues of mq plus 2m plus I3 is equals to, yes, M be 3 cross 3 singular matrix, and suppose that 2 and 3 are eigenvalues of M, then the number of linearly independent eigenvectors of m cube 2m plus I3. So friends, eigenvector eigenvalues of M equals to 0 to 3. So m cube plus 2m plus I3 eigenvalue is 1, and after that 8 plus 4 plus 1, after that 27 plus 6 plus 1. Distinct eigenvalue eigenvector, distinct eigenvectors equals to distinct eigenvalues. So number of linearly independent eigenvectors equals to 3. Now V equals to 1 comma 1 comma 1, and W equals to span of 1 comma 1 comma 0 and 0 comma 1 comma 1. So x comma y belongs to capital R. Let x 1 comma 0 plus y, same category problem friends, 0 comma 1 comma 1, and belongs to also W, the span, and distance d equals to d square equals to x minus 1 whole square plus x plus y minus 1 whole square plus y minus 1 whole square. Now d by capital D x ddx del by del is very writing del by del x del d into del x equals to, we get 2 into x minus 1 plus 2 into x plus y x plus y plus 1 equals to 0. So we get in here x equals to, we get x equals to 1 and del into del d by del y equals to 2 into x plus y minus 1 plus 2 into y minus 1 equals to 0. Get the value x equals to 2 by 3. Y equals to, we get 2 by 3, and now putting this value, the equation b square is equal to 1 by 9 plus 1 by 9 plus 1 by 9, and that is 1 by 3. So 3d square equals to 1 equals to 1. Next, Q27. Given two n cross n matrices A and B with entries in C, consider the following statements. If A and B have the same minimal polynomials, then A is similar to B number P, and if A has n distinct eigenvalues, then there exists, if A has n eigenvalue, U belongs to C to the power n such that U A U square U A to the power n minus 1. This is I have to prove. I have to find out. So MA equals to minimal polynomial, both are equal. So suppose this value is equals to x into x minus 1. A can be written this way. For example, 1 0 0. This is one example. And another example, B equals to 1 1 0. Okay. So friends, whatever you see that when equal is dimension of solution space is similar. So A and B same minimal polynomial. Then A is similar to B. A is similar to B when JC blocks are equal. If JC block are equal, then we can say that it is similar. So x into x minus 1, we take 3 cross 3 matrix, 3 cross 3 matrix, and we see that this is, it can be possible this way, x into x minus 1. So if we putting this x minus I, this is also 0, this is also 0, but it is not similar matrix. So friends, this problem, this statement is wrong, that minimal polynomial have same minimal polynomial, but it cannot be similar. A is similar to B if minimal polynomial are equal. This is not possible. So minimal polynomial as A is similar to B when JCF are equal. Characteristics polynomial. Now we will discuss next problem. So let's discuss that A has n distinct eigenvalues, and then U belongs to C to the power n such that a square U, a to the power n minus 1 U are Li. This is obviously correct. This is correct. So I just prove it is correct. A is n cross n matrix, and lambda I does not equals to lambda j. This is also correct. No problem. U comma a u comma a to the power n minus 1 u are Li. Li. So A is diagonal proportional to similar to D, means diagonal of lambda 1, lambda 2, lambda 3 up to lambda n, and it can be written u du up to dn minus 1 u. So it is a1 z1 z2 up to zn plus diagonal lambda 1 and lambda 2 up to lambda n z1 z2 to zn, and plus an diagonal lambda 1 comma lambda 2 lambda n n minus 1 z1 comma z2 zn. So it can be write it in the equation forms is u1 plus a1 lambda 1 plus an lambda n whole to the power n minus 1 is the a2, and after that a1 plus a2 lambda 2 plus an lambda n whole to the power n minus 1 equals to 0. Dot 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 dot, all the values is an plus a a1 a2 lambda 2 plus n lambda n whole to the power n minus 1 equals to 0. That is 1 1 up to 1 lambda 1 lambda 2 lambda n. It is lambda 1 whole to the power n minus 1, not lambda n. It is lambda 1, it is lambda 2, it is lambda n. Write this way: lambda 1 whole square, it is lambda 1 lambda 2 whole square to lambda 2 n to the power n minus 1 lambda n whole square lambda n whole to the power n minus 1. This is my total value. This value is does not equals to 0. So my eigenvalues are Li, linearly independent. So hence I can say that A has n distinct eigenvalues and U belongs to C to the power n, such that U, AU, A square U or both are Li. Because distinct, must remember, distinct eigenvalue. Distinct eigenvalues means diagonalizable. If, must remember, if eigenvalues then it is diagonalizable. Now we start next problem. Our next discussions: nature of a quadratic form. A quadratic form, a real quadratic form x dash ax in a valuable is said to be positive definite if all eigenvalues of a greater than. So quadratic is x dash a x. This form are this form are quadratic form when all the eigenvalues of a greater than 0. Negative matrix if all the eigenvalue of a less than 0. Positive semi-definite if negative semi-definite if all eigenvalues of a less than or equals to 0. So question number 28. The matrix 3 minus 1 minus 1 2 1 0 minus 1 3 is positive definite, non-negative semi-definite, but not positive definite, negative definite. So friends, I have to check this eigenvalue. So friends, in here you see that the question is positive definite. So we have to find out all the eigenvalues are positive or negative. So let's write the matrix 0 minus 1 2 minus 1 0 minus 1 and 3. This is my matrix, and eigenvalues is 3 2 3. Eigenvalues is 3 2 3. So number 1, all the eigenvalues are greater than 0. This is write down, this is A, and AT equals to AT, sorry, it is not eigenvalue, sorry, it is eigen not value, it is the coefficient, major principal of minor, greater than 0, principal of minor, it's the principal of minor. AT equals to AT equals to 3, 2, 3, minus 1, 0, minus 1, minus 1, 0, 0. So whatever we see that AT equals to A, and AT equals to A means this proof that all eigenvalue are all eigenvalue are real. All eigenvalues are real. So AT is equal to A. So all eigenvalues are real, and principal minor is greater than 0, is positive, and minority is 3, 3 minus 1, minus 1, 2 equals to 5. This portion 3, when we collect, then it is this portion. This portion is this way. So this is the 5, and 2 minus 1, minus 1, 3 equals to 5, and 3, 0, 0, 3 equals to 9, and our determinant portion, determinant equals to 12. So it is greater than 0. So that's why we can say that as a triple product, so it is positive definite is eigenvalue, another is everything is. So whatever we see that this portion is positive definite as eigenvalue are positive. How we judge this is eigenvalue? That symmetric as a symmetric matrix, so all eigenvalues are real, and number 3, that we see that all principal minor are greater than positive, and we see that cofactor are also positive. So so the and so the eigenvalues is positive. Otherwise you can solve this process, characteristic equation you can find out, and also you can show up the lambda eigenvalues. So very simple problem, friends. Now we are solving this problem. Let f such that r square tends to r square be given by f x y equal to x square plus y square plus sin x. Then the derivative of f at x comma y is linear transformation is d f x comma y is equal to df x y is equal to, we can write this way, f1x, f2x, and f f1y, f2y. This is the process. Okay friends, I hope f2y and f2y, sorry, f1y and f2y. This is the x, this is the x variable, this is the y variable, f1y, sorry. Now, so first term is fxy. I write fx comma y equals to x square comma y square plus sin x. So this is f1. I can say this is f1. This is f2. So f1x equals to, I can write 2x, and after derivative with respect to y, so it is 0. And f2 is, this is cos x, and after that 2y. And point is a comma b. So my directional derivative is 2a comma cos a and 0 and 2. Procedure is this way: f1, f2, f3, and x, y, and z. This is the procedure. So f1, you will write derivative of f1x, f1y, f1z, f2x, f2y, and f2z. Similarly, f3 you can find out. This is the process. I hope I can clear this concept. Number 2, directional derivative problems, friends. A function f such that r square tends to r is defined if fxy equals to xy, let v equal 1 comma 2 and a1 comma a equals to a1 comma a2 be two elements of r square. The directional derivative of f in the direction of v at e is. So how the problem, friends? This is very simple problem. F1, this is the, I can write fxy only 1 equal to xy. So d of x comma y equals to, I can write this way, that is f1x and f1y. So I can write, here is function is only one, not 2 3. So I can write this way, only one function. So it is after derivative we can get f1x, fx means this is y, and fy is equal to x, and multiplying with d a1 a2 equals to y comma x and 1 comma 2. So this is the must remember. 1 comma 2 is v, so my direction xy, and let v equals to 1 comma 2 and a is equal to 1 comma a2 be two elements of r square. So the directional derivative, so 2 point we get, so I can multiply with this 1 comma 2, so it is 2y plus x, and under the point a1 comma a2, and I can write this is 2a1 plus a2. So my okay, sorry, this matrix multiplication is wrong. My multiplication is wrong, so it is 2, so this is a1, so a2 plus 2a1, a2 plus 2a1, this is the formula. Now the question is that which of the following subsets of r to the power 4 is a basis of r to the power 4. So b1 equals to 1 0 0 1 1 0, this is b2 equals to this, b3 equals to this. So how, so let's see, b1 equals to this way, I can write 1, after that you can write this way, okay, no problem, 0 0 0 and 1 1 0 0 1 1 1 1 0, and this is the, and you see the date b1 equals to, does not equals to 0, so it is a line. This portion is linearly independent, and b2 equals to 1 2 double 0 1 2 3 double 0 1 2 3 4. Now you can see this is also a line, because date b2 equals to 0, rank 4 does not equals to 0, sorry, does not equals to 0, date, so rank is 4, rank 4, and its rank 4. Now let's see that b3, this is, these two are base, basis of r to the power 4. Now we will solve b3. b3 can be written this way, 1 2 0 0 and 0 0 1 1 2 1 0 0 minus 5 5 0 0. So friends, it is easily see that this is b3, and date of b3 equals to 0, that equals to 0, so it is not Li. So my this option is totally wrong and this option is correct. Consider matrix A equals to cos theta minus sin theta sin theta. Cos theta sin theta and minus sin theta now a to the power 500 2015 we have to find out. So how can we find out this? So lambda is equal to obviously cos theta plus I sin theta, this kind of problem. As the characteristic equation is minus 2 cos theta plus 1 equals to 0. So lambda 1 plus lambda 2 equals to lambda 1 plus lambda 2 equals and lambda 1 minus lambda 2 equals to 2I sin theta. So what we get? We get lambda equals to cos theta plus I sin theta. So similarly lambda 1 and lambda 2 will become cos theta minus I sin theta. So lambda 1 to the power 2015 equals to cos 2015. Theta means 2 pi divided by 31 plus I sin 2015 into 2 pi divided by 31. Now 2015 divided by 31. So we can write if we will divide it, then it's this value will become 1. Okay, this value is become 1 and lambda 1 and lambda 2 equals this value is also 1. So let j be the, so thus we can say that a to the power 2000 equals to I. This is the identity element, friends. And let a be n cross n with each entry equal to plus 1, 1 and 0. Each such that every column that exactly plus 1 and exactly minus 1. We can conclude that rank of A less than equals to n minus 1, rank of A is equal to m, n minus 1 greater than equals to m, n less than equals to m. So how can we find out? So let's see that A is n cross m and every column has exactly every column has exactly plus 1 comma minus 1 comma 0 0 entry. Okay, no problem. If the column has plus 1 minus 1 and 0 entries, so 0, suppose this is my 1 1 1 1 1, this is the possibility, and was a matrix. So every column, each entry equal to plus 1 1 or 0. So every column has exactly plus 1 exactly minus 1. So every column, so it can be possible this way, otherwise 1 0 1. So we can conclude that n cross m row and column. So friends, here say that each column should have 1 minus 1 minus 1 and minus 1. So 0 is also entry. So 0 should be in here, in here, in here, in here. So n less than equals to m cannot be possible. Rho is less than equals to m. This is not possible because 0 should be entry. Every column and every column and every, you see that every column has 1 and minus 1 entries, means 2 digit always entry. So how can n less than equals to n? N means in here row less than equals to column. This is possible in here. You see that it is column 1 2 3 4, 4 column 4, and row is column is in here 4 and row is 3. So it is not less than equals to, it is 3 less than 4, but it cannot be possible n equals to m. It is not. So this condition does not hold. Equals to n less than equals to does not hold. So it is not, it cannot say, it can write, it can be written this way. So it is not exactly hold, and rank of a equal to n minus 1 less than equals to, this is possible because 0 is eigenvector. 0 is my eigenvector. So rank a less than equals to n minus 1 and rank a equals to m. rank A equals to M. This is not possible. And n minus 1 less than equals to M. This is not possible. So rank is less than column. A column is dimension, total dimension is dimension equals to M. Rank is equal to nullity plus rank is equal to M. Now rank A nullity is nullity should be M minus N, so minus 1. So then dimension equals to M nullity, rank nullity theory, nullity plus rank is equal to dimension. So we cannot say that n minus 1 less than equals to M, because you can get less than n minus 1 less than rank of A is always less than equals to n minus 1. Okay, this is. And another problem is that let J denotes the matrix of order n cross n with all entries 1, and let B is 3 cross 3 n cross 3n matrix given by B equals to 0 0 0 0 j j, and then rank of B is. So friends, you see that J matrix means all the entry is 1 1 1, and this is J matrix is n cross n. So n cross n means eigenvalue and 0, not 1, sorry, eigenvalue is n and 0. Now then the rank of B is rank, how many rank is possible. So it can be written this way: 0 1 1 1 1 1 1, this way. So if we find the rank of J, rank of J equals to 1, so 3 1, so total is 3, rank of J. Next problem, friends. J matrix has rank of J matrix, rank of J matrix is 1. Now let's start. Let A be n cross n non-singular matrix with real entries, and let B equals to AT denote the transpose of A which of the following matrices are positive definite. A plus B, A inverse plus B inverse, AB, AB, A. So non-singular matrix A is n plus n non-singular matrix with real entries B equals to AT. Denote denote the transpose of A. Which of the following matrices are positive definite? So non-singular matrix real entries. So det of A does not equals to 0 and A is n plus n matrix and B is A transpose. So A inverse and B inverse the eigenvector, suppose it is not telling that it is positive or negative. So A transpose means both have same lambda. Lambda is eigenvalue of lambda is value of lambda is eigenvalue of B because transposition have same eigenvalues friends. So when A plus B, it can be positive definite, maybe negative definite, but AB is equal to lambda square. AB equals to this, obviously positive, greater than 0, real entries. So only number 3 is correct. 4, 2, option 1, both are wrong because ABA equals to lambda cube. It may be positive, maybe negative. This is obviously positive definite. Now let A equals to Aij be n cross n matrix such that Aij is an integer for all I comma j. Let equals to I, B equals to Bij, where I is the identity for a square matrix C. Let C denotes is determinant. Which of the following statements is true? Number 1, let A equals to 1. So friends, whatever is say that AB equals to I, B equals to Bij, A equals to AI. So A equals to Aij such that Aij belongs to Z, and for all I comma and AB equals to I, so B equals to Bij AB equals to I, so date of A, date of AB date of AB equals to 1, date of AB equals to 1, so date of A into date of B equals to 1. So if date of A equals to 1, then date of B equals to 1. That implies date of B equals to 1. So friends, my first option is correct, that if date of A equals to 1, then date of B equals to 1. Number 2, a sufficient condition for each Bij to be an integer is that date A is an integer. So friends, let date of A equals to Z minus 0. That implies date of B equals to 1 by date A, and so that this is not mean that A is sufficient condition that Bij is integer, so that date A is integer, this is not possible, because A B equals to I, so B equals to A inverse, and A inverse can be written adjoint A divided by A date A, so it can be written this way, that A by B, and something, this is the rational number, this number is Q, but not, it may be, it not be integer, so this portion is wrong, and B is always an integer matrix. This portion is also wrong. And number 4, that a necessary condition for each B is date A belongs to minus A, minus 1, and plus 1 plus 1. This is always correct. Let's start to solve number 37. Question number 37. So I hope that I solve every questions, every facts I solve. So also video notes I will provide every groups. And number 37, question number 37. A equals to 1 1 0 a to the power n tends to alpha n comma beta n, and date of alpha n less than equals to date of beta n. The condition, friends, this condition I just mark. This condition I just marks two eigenvalue alpha a to the power n, b to the power n, and characteristics equation of a equals to x square minus x plus 1, and x is equal to 1 plus minus root over 5 by 2. This number I think Fibonacci number. So alpha n equals to 1 plus root over 5 by 2 whole to the power n, and beta n equals to 1 minus root over 5 divided by 2 whole to the power n, and alpha n. So alpha n tends to, if n tends to infinity, so alpha n tends to 0. This is possible, this is possible, this is sorry, alpha n tends to infinity because alpha n greater than 1. So this is possible. So n tends to infinity, alpha n, this is correct. Number 2, beta n is positive if n is even. Beta n is positive if n is even. This portion is also correct. So beta n, suppose beta 2 is equal to 1 minus root over 5 divided by 2 whole square. So it can be written 1 minus 2 root 5 plus 5 divided by 2, and it can be written 3 minus root over 5, and this is greater than 0. So it is possible because n is even, and beta n tends to infinity. It is not infinity, it is 0. It should be 0, so it is correct. And beta n is negative if n is odd. This is also correct. I hope I can clear this concept. Next I will solve number 38. Let Mn denote the vector space of all n cross n real matrices. Among the following subset of Mn, decide which are linear. V1 equals to A equals to Mn, A is non-singular, V2 is equal to A belongs to Mn, and V3 equals to A belongs to Mn, and V4 is equal to Ba, and where B is some fixed matrix. Solution, let's try to solve. Solution, Mn such that n cross n is a real matrix, and V2 equals to A belongs to Mn such that date of A equals to 0, and A equals to 0 0 1 1 and b equals to minus 1 comma 1 0 0. So decide the linear subspace. So we can't say that date of A plus B does not equals to date of A plus date of B, so that number 1 is not correct. Number 2 is not correct because date of A equals to 0. This is cannot be possible because we have already told A plus B does not equals to A plus B. So this is not possible, and trace of A equals to 0. This is correct, and before equals to B, where B is some fixed matrix, this is also correct. This is true and this is also true. How they are true, friends? Because trace of P alpha subspace rule V1 plus beta V2 equals to alpha T V1 plus beta T V2, the trace. So if trace of alpha A1 plus trace of alpha 2 A2 equals to alpha 1 trace of A1 plus alpha 2 trace of A2, so equals to 0. Similarly, V4 equal to BA such that A belongs to Mn and 0 belongs to also V4, 0 also belongs to V3, A1 comma A2 belongs to Mn, so alpha B A1 plus beta B A2. So it can be written this way: alpha B alpha A1 plus B beta A2. Sorry, this writing is beta, this is capital, and it can be written, it is also belongs to Mn, so this is vector space. Now we will solve next problem. PQ is equal to minus QP, and that implies PQ P inverse equals to minus Q P P inverse, and PQ P inverse equals to minus Q. So PQ P inverse is similar to minus q, and okay, similar to minus q, no problem. So trace of q equals to trace of minus trace of q. So 2 trace of q is equal to 0. So my my first option is correct. Trace of p is equal to trace of q, and trace of p equals to minus trace of q. This is not possible. Trace of p is equal to trace of q is equal to does not equal to trace of q. Can't say this others option are all wrong. Next, this problem is let w1, w2, w3 be three distinct subspaces of R10 such that wi has dimension 9. Let w is equal to w1 intersection w2 intersection w3. Then we can conclude that w may not be subspace of R10. W dimension of w less than equals to 8. So our formula is that wi is given is dimension of 9, and this is the dimension of w I is equal to dimension is equals to 9. Sorry, it is 9, where I equals to 1, 2, 3. This is given, and we know that dimension of w1 intersection w2 intersection w3 less than equals to dimension of w1 plus dimension of, this is the formula, plus dimension of, this is the result. This result is dimension of w3 minus 2 into dimension of 10. So what can I don't know the dimension of w1 in, so this value is dimension of w. I can write dimension of w intersection less than equals to dimension of w1, dimension of w2, w3 both are 27 minus 20 equals to 7. So my this option is correct. Is that w may not be a subspace of R10. This is also wrong. And dimension of w less than equals to 3. This is wrong. So now we will our calculation is large that w1 equal can be written as x belongs to r r and xi belongs to, there should be a restrictions I equals to 2 to 10, means it can be written x1 equals to I equals to 2 to 10 xi, and x belongs to r to the power 10 x2 equals to I equals to 2 I equals to 1 comma 3 comma 10 xi, and x belongs to R10, so such that x3 equals to I equals to 1 comma 2 up to 10 xi. So friends, if write this way, that my object is this way, okay, 1 2 up to 1, this is 10 cross 10 matrix, and after that this is 1 minus 1 up to 1, and another is 1 1 minus 1 up to 1. So see that we see that our number of li means free variable is 2, free variable. So this is the our our kernel, so it should be 10 is my dimension, so 10 minus 2 is equal to 8. So dimension of w less than equals to 8, because you see that two are li linearly independent. We see there is two vectors are li, means free a variable is 2, we can see, and two, and another is the pivot is only 1, pivot element is 1. So we our pivot element is 8. So we see that the 10 minus 2 is our 8. So dimension should be 8, less than equals to 8. This way to be a real symmetric matrix, then we can conclude that A does not have 0 as an eigenvalue. All eigenvalues of A are real. If A inverse exists, then A inverse is real and symmetric. A has at least one positive eigenvalue. So real symmetric matrix, real symmetric matrix, we cannot say that it does not have zero eigenvalues. We cannot say, because real symmetric matrix the eigenvalue of real symmetric matrix is eigenvalue of real symmetric matrix is real. So 0 may be our eigenvalues. So all eigenvalues A are real. This is 100% correct. If A inverse exists, then A inverse is real and symmetric. This is also correct. A has at least one positive eigenvalue. It is not possible. It is maybe all eigenvalue is negative. So we can say that only one positive eigenvalue. Next is that consider the subspace. Consider the subspace W1 and W2 are 3. W1 is equal to x, y, z, x plus y plus z, and W2 is this. So if W is a subspace of R cube such that W1, W2 is span of 0, 1, 1, and W1 intersection W2 is orthogonal to W intersection W1 with respect to the usual inner product of R cube, then W equals to. So see that W belongs to 0, 1, 1. So and XYZ W intersection W1 and 0, 1, 1 equals to 0 because it is the, must remember, orthogonal W intersection W1 and W intersection W2. So we get y plus z equals to 0. Let 1, so z equals to minus 1. So my basis is 0, 1, minus 1. So W is span of 0, 1, and 0, 1, 1. This is the answer. Question number 43. let C equals to 1 by 2 be a basis of R square, and T such that R square be defined by T x comma y and x plus y exponents to y. So if TC represents the matrix of T with respect to the basis C such that T of C. So T equals to 1, 2, T1 2 equals 1 plus 2 and 1 minus 4, that equals to 3 minus 3, 3 minus 3, and that equals to A plus 1 comma B into B into 2 comma 1. I can represent linear transformation. So this way I can write, and T 2 comma 1 can be written this way 3 0, and that implies A 1 2 and plus B 2 1. So A plus 2B equals to 3, and and 2A plus B equals to 1. From this equation, A plus 2B is equal to 3, 2A plus B equals to minus 3, So A equals to minus 3, and B equals to, so I get the, so friends, my TCE equals to with the C comma 3. After that, we have C and D. So let's see that C plus 2D equals to C plus 2D equals to 3, and D 2C plus D equals to 0. So I multiply, just it is 4 into 2D. So 3C minus 3C is equal to 3. So C is equal to, okay. So 1 minute. I have to check. C plus 2D, C 2D, and 2C plus 2D plus 2C plus D equals to 0. So minus 3C is equal to 1. So D equals to minus 1 plus 2D equals to 3. So D equals to 1. So my value is minus 1 comma 1. I can write this way. Sorry, no. D equals to 2. So my answer is C is equal to 2. So I can write this way. With respect to basis, PC is equal to C comma minus 3 and minus 1 comma. In here I did mistake that free variable is in here I did a mistake. In here free variable is 8. So free variable is dimension is number of free variable. So dimension is let w1 w1 equal to u plus v plus w, u plus vw, 2v plus x, 2u. Among the following is true, w1 equals to 1. So dimension okay, there is the question is not given, and w2 equals to u v comma w comma x belongs to r to the power 4 such that u plus w plus x equals to 0, u plus w and v minus x equals to 0. This is my total. This is my w2. So dimension equals to free variable, number of free variable. So a equals to 1 1 0 and 0 1 and 2 0 2 minus 1 it can be written 1 1 1 0. Imagine 0 1, sorry, not minus 1, this is, and 0 minus 2 0 minus 1. Now it can be written this way: 1 1 1 0 0 2 0 1 and 0 0 0 0. So you see that pivot element is only one. Pivot element is only one, and 1 and 2. So free variable equals to 2. Free variable equals to 2. So dimension of A equals to 2. So dimension of W1 equals to 1. This option is wrong. Dimension of W1 I have to take. And similarly, you see that B equals to 0 1 1 0 1 0 minus 1 and 0 0 0 minus 2. So our pivot element is minus 2. So free variable is 1. So dimension of B 1. If you see that you can say number of restrictions, you say the dimension of B, number of elements minus number of dimension of B equal to number of elements minus minus restriction. This way you can find out. So restriction is number that is 3 minus 4 minus 4 minus 3 equals to 1. This way you can find out. So dimension of B equals to 1. So dimension of W2. Now I have to find out dimension of W1 plus W2 equal to 3. This option I have to check. In here, free variable free variable in here free variable equal to W and X. Here free variable is 1, only W. So W intersection of W2 equals to 1, dimension of W1 intersection of W2. So this option is correct, And this option is wrong because 2 plus 1, 2 plus 1 minus 1 equals to 2, but it is wrong. So friends, we go to solve next problem. Span. Let V be a closed subspace where equal to 0, 1, and let f, g equal to L square 0, 1 be given by fx equal to x, gx equal to x square. If V orthogonal of V is equal to span f and Pg is the orthogonal projections of G on V, then G minus Pg x. So how can I find out? So let V be the closed subspace L square. Okay. So we know that projections formula equals to PB, capital P B equal to A comma B divided by A comma A into E. So here A equals to X and B equals to X square. So X comma X square equals to integration 0 to 1 x cube dx. So it will get the value is 1 by 4. Similarly, x comma x equals to integration 0 to 1 x square dx, so that our projections orthogonal projection is g minus pg x equal to 3 by 4 x. So my answer is number A. Thanks for watching. I hope I can clear a lot of concepts.